All right, so we've been talking a lot about two variable vector fields. What about three variables? How do we decide whether or not a three-dimensional vector field is conservative? Well, what we're going to do first is give a definition, and it's just kind of an easy way to store some important information about our vector field. So let's say that we've got a vector valued function f of x, y, z. That's mi plus nj, and then now plus pk. So we have an extra k component, that z component. We're going to define the curl of this function. A common notation to kind of help you remember the definition is we use that del that was from the gradient, and we're going to cross it with that vector field f, with that vector valued function. Now this del, it really isn't quite a thing on its own, it's actually an operation. So what this is going to look like, we have to remember the setup of a cross product. So the setup of a cross product is this determinant style. The top row is ijk. The second row is supposed to come from the first vector in the cross product, which in this case we've replaced with del. And what we mean by that is del is this placeholder for the individual partial derivatives. So there's just going to be operations here waiting to be applied to different expressions. So the partial with respect to x, the partial with respect to y, the partial with respect to z. And then the third row is the components of f, so m, n, and p. And then we're just going to use that format for how we compute that determinant. So we first use the I, and we cover up its row and column. So now what happens, instead of multiplying, we're really using the operation. So this is saying take the partial with respect to y of p. So the partial of p with respect to y, and then minus, take this partial of n. So the partial with respect to z of n. That's going to be the I component. So that's times I. And then remember you do minus the j component. So you cover up the row and column of j. And then so the main diagonal says take the partial with respect to x of p. And then subtract the partial with respect to z of m. So we've got the partial of p with respect to x minus the partial of m with respect to z is all times j. And then we add that to the z component, so cover up the last row and top column. So the partial with respect to x of n minus the partial with respect to y of m, all times k. So if we just try and memorize the last row, there's a lot of really particular orders, right? Which ones go with the different components, which ones go with I, which ones go with j, which one's first and second that gets subtracted and added. So this way of storing all of the information in that cross product form is useful and helpful. So that's what that means, to say the del crossed with f really means ijk, the partial derivatives, operations waiting to be used, and then the m and p, the components of f. So then our theorem is that in 3 dimensions, the vector field f of x, y, z is conservative if and only if the curl of f is the 0 vector, which to be the 0 vector would mean all of these components are 0, which to be 0, you can think about that would mean that these two partial derivatives really need to be equal so that they subtract to 0. These two need to be equal, and these two need to be equal. So we still are trying to use different ideas of if these really did come from the same function, and the m, the n, and the p really are like a partial with respect to x, a partial with respect to y, and a partial with respect to z. Well, then all of this really makes a lot of sense, right? This is saying the partial with respect to y of the partial with respect to z should be equal to the partial of y now taken with respect to z. So those should be the same if they came from the same place. These two should both be the partials, the mixed partials with x and z, and these two should be the mixed partials of x with y. Is really where they would be coming from. So if all of those are the same, it kind of means that they came from the same function. So That's what we mean by all of them being 0. So let's try and practice it. Determine whether or not capital F of x, y, z, which is the vector 2xy, x squared plus z squared, and 2yz is conservative. So we're actually going to do this by computing the curl. So we're going to find curl of F, which is that del crossed with F of x, y, z. So we're going to set that up as at determinant form, so ijk. Del is the placeholder for those operations, partial with respect to x, partial with respect to y, partial with respect to z. And then the f vector goes in the last row, so we need those components, which were 2xy, and then x squared plus z squared, and then we need 2yz in the last component. And we're going to compute this like a cross product. So first we need to cover up I. So we'd have the partial with respect to y of 2yz. I'm going to write it out. Partial with respect to y of 2yz minus the partial with respect to z of x squared plus z squared. These are all the component I vector. We then do minus, cover up the j row and column, so the partial of x of 2yz minus the partial of z of 2xy. Those are all the component of the j vector. And then we add the components of the k vector, so cover up the top row and last column. We'll get the partial with respect to x of x squared plus z squared minus the partial with respect to y of 2xy. And this is all the k component. So now we need to find those partials. So the partial with respect to y of 2yz is going to be 2z. Then minus the partial with respect to z of x squared plus z squared is also 2z. So we're looking good so far. Now we've got minus partial with respect to x of 2yz. Well, that's just 0. There is no x's in there, so we'd have minus 0 minus the partial with respect to z of 2xy is also 0. So also looking good there so far. And then now we've got the last one, the partial with respect to x of x squared plus z squared is going to be 2x. Minus the partial with respect to y of 2xy is also 2x. And that's our k component. So really we have 0 times I minus 0 times j plus 0 times k, which is in fact the 0 vector. So by our theorem, f is conservative because the curl equals the 0 vector. So f is conservative. Which is pretty awesome. So it looks like a lot, but really it's just doing a lot of derivatives and making sure we do them in the right order. So we'll definitely, you'll practice this lots and we'll look at other things again about it. But keep in mind this cross product notation does really help us keep track of the order to do things in.